Alpha Houston on space to ground 1 for Don. We're ready for your downlink.
Okay, I'm going to hit play.
I'm Don Pettit. I was fortunate enough to be science officer on Expedition 6 to the International Space Station. And during this expedition, we had several kinds of science that we did. We did programmatic science, which is well-planned and well-thought-out science, comes up from the ground and is orchestrated from the ground. And then we have science of opportunity. And this is science that is done at the discretion of the scientists on board space station. And this is kind of the discovery science. And during our mission, we called our science of opportunity Saturday morning science. Viscoelastic fluids have to be one of the neatest things for kids to play with, because it's the fancy way of talking about slime and goo and all kinds of other things that you see kids playing with. A viscoelastic fluid is a fluid that has both the viscous properties of a fluid and the elastic properties of a solid. So you could think of it as kind of a fluid rubber band, something that can behave like a liquid, but it can also be a little bit stretchy like a rubber band. So it's got some of the elastic properties of a solid, some of the viscous properties of a liquid. And of course, you can see that this makes the traits for all the slime and other kinds of goo that little kids like to play with. And we had some of this on space station. And what we see here is a shampoo. Many of the shampoos have viscoelastic properties. And I took some of the shampoo we had on space station, and we will see some viscoelastic effects demonstrated here. Here we see a liquid column of shampoo, about 10 millimeters in diameter. And this column is short and squat and is stable. And you're seeing it in this video image. It doesn't look like anything's happening because nothing is really happening. It's just sitting there, and it'll sit there for hours. Now we see the same cylinder of shampoo, but it's been lengthened. And it's longer now than 3 times the diameter of the cylinder. And a fellow by the name of Lord Rayleigh developed some stability criteria for liquid cylinders and showed that if a cylinder is shorter than 3 times the diameter, it will be stable and it'll just sit there. But if the liquid cylinder is longer than 3 times the diameter, it will break apart. And what we're going to see here is an example of this Rayleigh instability set up in this cylinder made from the viscoelastic fluid from our space station shampoo. So let's watch this video now with this cylinder that is time-lapse over a period of about a half hour, and you can see the instability slowly take place and tear this cylinder apart, and it pinches it apart into 2 droplets. So again, there we saw a short cylinder just sat there. It didn't even look like it was moving because it wasn't moving, but you make the cylinder longer than 3 times its diameter, and now the Rayleigh instability will take place and will make it come apart. And you can see this in 1G. However, the weightless environment of space allows you to observe this over a long period of time and take time-lapse movies and look at the details of what's happening as this liquid cylinder breaks up. Now, another property of viscoelastic fluid is called dye swell. And we're going to see this in the next video clip. And this happens with many high molecular weight polymer systems. If you extrude a plastic out a nozzle that's 10 millimeters in diameter, the column of plastic going out from this nozzle will be larger than 10 millimeters. It might be 14 millimeters in diameter. It might be 15 millimeters in diameter. And they call this dye swell. It's a well-known phenomenon. Engineers that deal with extruding polymers, making plastic objects know about dye swell. They have to in order to be able to make something, a final product the size that they want. And you can see this with viscoelastic fluids as well. If you squirt them out a nozzle, you can see that the diameter of the stream exiting the nozzle is larger than the diameter of the nozzle itself. But it's harder to see in the fluids because acceleration forces due to gravity disrupt the flow as soon as you squirt a fluid out a nozzle. And what we're going to see here in the weightless environment is this shampoo being extruded from a nozzle. And because there's no acceleration forces disrupting the downstream flow of liquid, you can see the onset of dye swell happening. So let's go ahead and roll the video and watch this. As it's exiting the nozzle, it will maintain the diameter of the nozzle for a short distance, and then all of a sudden, puff, the dye swell will occur, and you can see the resultant stream is about a factor of 2 larger in diameter than the nozzle that it was squirt out of. And from this, we can see the actual kinetics. We can see the dynamics of dye swell. And as the fluid stream is sped up, the dye swell gets pushed further away, and as the stream is slowed down, the dye swell will move back and actually attach itself to the edge of the nozzle. And I found this fascinating. From this video, you could get rough idea as to the time constant for the onset of dye swell. If a cylinder is shorter than 3 times the diameter, it will be stable and it'll just sit there. But if the liquid cylinder is longer than 3 times the diameter, it will break apart. Now, another property of viscoelastic fluid is called dye swell.
And Houston Alpha, that's it for our Saturday morning science.